Yes, sir.
Fine. So, okay, we will start. I think people are not joining. Fine, so we will start. Uh, First, we will start with the recap of all the lectures that professor has taught this week, and then we will solve the sample assignment given on the site. Let me see. Yeah. So the non-graded assignment we will solve that, and then we will look at some sample problems if time permits. Okay, fine. So everyone is able to access the lectures, like last week's lectures on YouTube and the accompanying codes, right? Fine. So let us first start with approximations and round off errors. So as we know that the course is numerical methods for MATLAB for numerical computations. So we'll be looking at the some of the numerical methods to approximate the differentiations of some functions, integration of functions, as well as PDEs and ODEs. So we need to know how accurate our approximate results are compared to the true ones. So that is where the errors and the errors come into place. So mm we have seen like there are different types of error. Is someone wants to join? Yeah, so we have seen that there are a number of errors. We have round off errors, we have truncation errors, and then there is this machine precision. So due to machine precision also some of the data is usually lost because we round off the some of the insignificant digits to the nearest integer, right? So first, let us differentiate between accuracy and precision. So you can see this graph over here. So on the y-axis we have increasing precision, and on the x-axis we have increasing accuracy. So most of you must have seen this graph during your 12th class or first year of engineering. So the first one is where we have the least accuracy and least precision. So the true value is somewhere around the center of the this image, and as we go away from this circular region, this center and this circular regions, our accuracy decreases and since these all of these values are also scattered, they are not concentrated on one point, so the precision is also not there. So precision basically means the reproducibility. So how close is a computed value to the previously computed value? So each of these values, like I have some value over here, then I have some value over here. So these values are not close to one another. Just go to- Fine. So these values are not close to one another. Each of the values are at different positions. So the result is not very precise, and at the same time we have true value that is lying not lying with that is at the center of this circle. So each of these values are not close to the true value, so the result is neither accurate. Then as we go to the B figure, then we can see even though the precision is not that much, the results are closer to the true value. Like the first figure is the first point, calculated point is at the center. Then these different these different circles are the different accurate radius of accuracies. So we have something called as radius of accurate radius of accuracy. So the smaller the radius of accuracy, the more is the accuracy. So this is the this if the points are in this circle, the second circle, then our accuracy is less than the all the points then that are those are in this circle. So as we go away from this circle, our accuracy decreases. But at the same time, since we have the same accuracy on all the points which are on this circle, so we can say the result is still accurate compared to the previous results, because here the all of these results are shifted from the mean value, like by a lot. These are evenly distributed along the radius of this along the circumference of this circle. So this is much more accurate than the points plotted in figure A. Next, if we go to the figure C, then that is basically our accuracy is very less. Accuracy is very poor, but our precision is very high, because all the points are concentrated along a single area. Then there is the D figure, where the results are accurate and precise. So all the results are closer to the true value, as well as for all the different results they are close to one another also. So this result is accurate as well as precise. So there are these two measurements: how accurate is your result and how precise is your result. So this is what we mean by accuracy and precision. Then we have two more points: inaccuracy or a systematic deviation from the actual value. So this result is very inaccurate. Then we have imprecision or in uncertainty. So the magnitude of scatter, like the scatter over here from the true value is very large, but at the same time it's also very inaccurate. In this figure, the inaccuracy is not very high, because the deviation from the actual value is there, but it's not scattered all around the place. It's concentrated, but there is a lot of imprecision, because the magnitude of scatter is very high over here. Then in this place we have inaccuracy but precision, because the magnitude of scatter is concentrated, but it's very far away from the actual value. In this one, the result is accurate as well as precise. Fine. So let us go to the next slide. Yeah. So now comes the topic of significant digits. So what do we mean by significant digits? It's the number of figures that can be used with confidence for calculation or for determining a number. So suppose we have this 53,800. So in this, it depends on how you want to write this number. Suppose if I want to write it in this type of format, so I have suppose I want to write it in this type of format, so I have 5.38 into 10 to the power 4. So I have three significant digits, 5, 3 and 8, and this 10 to the power 4, this is the base of the number system in which I am trying to write it. So it's a base 10 number system, and these are the significant digits. Suppose now I increase a 0 after 5.38. So if I'm trying to write a number in this type of notation, then all the zeros, even if there are no digits, after the zero, then also we count those zeros as significant digits. So in this case we have four number of significant digits. Similarly, if I increase one more zero over here, then the number of significant digits increases to 5. At the same time, if I just write these numbers as a decimal in decimal format without these scientific notation, then the zeros before the digits or after the decimal places, we don't count those zeros in this. So in this case, the significant digit stays at 4. Even if I remove one zero, so the number changes. So this number is different than this number, but the number of significant digits are still 4, right? Okay. Uh, Fine. So now let us see what are the sources of error for our approximation. So we have two sources of error: round off error, which is the error incurred when representing a number with fewer digits than are required to completely capture the exact numerical value. So suppose in this case, if the number is 5.3801 and I only write it as 5.380 into 10 to the power 4, so I have lost the last significant digit. So that information is lost now. So that is called my round off error. Then there is truncation error. So the error incurred when limiting the accuracy or the running time of a procedure that requires an impractical amount of time, possibly infinite, in order to obtain the exact true answer. So this is basically if we look at the Taylor series approximation of some function. So what is the pointer? So suppose I look at the Taylor series approximation of a function. So if I am only taking the first two terms of the approximation, then that is called my first order Taylor series expansion. So I am removing all the digits after the first term, after the first two terms. So I am truncating my Taylor series to only first two terms. That means I am losing some of the information which is being captured by later number of terms. So that is my truncation error, because I'm removing certain part of function in order to speed up my calculation. Because if I calculate all these functions, first derivative, second derivative, up to nth derivative, then all these calculations take up time. So to speed up my calculations, I am removing this information. I am removing these later terms, but at the same time, I am losing on accuracy also. So there is a trade-off between speed and accuracy, and we need to find a sweet spot. So if I look at the curve, so it is something like, as the number of terms increases, my computational speed also increases. But with more number of terms, my computational speed still increases, but my accuracy starts to decrease. So you need to find a trade-off between the number of terms that are required and the accuracy that you want to achieve. Fine. Further, we have some definition. So we have true error, which is like if x is the true value and y is the approximated value, then my true error is just x minus y. Absolute error, we take the absolute difference of these two terms and we get the absolute error. And relative error is how much is my error compared to the original or the true value. So I just divide the true error with the true value and I get the relative true error. And similarly, if I take the absolute of relative true error, I get the relative absolute true error. So we will be looking at some of these terms to see how, like in this Taylor series, how these error changes with the number of terms and these h values. Fine. Right, so let us look at this Maclaurin series for e to the power x. Maclaurin series is just a special case of Taylor series where we take a value of x to be 0 and h to be the number that we are trying to approximate. So in this case we are trying to approximate e to the power a. So I am taking x as 0 and h as a, and we are taking n number of terms. Okay. If I go to MATLAB, fine. So this is my code for a single Maclaurin series for a single value of a, and I am taking two number of terms. So I am first calculating the summation part, like 1 plus a to the square upon 2 factorial plus a cube upon 3 factorial. So this is the later part of that Maclaurin series. So the first term, if I have two number of terms, so the first one will give me 0.1 to the power 1 divided by 1 factorial. The second term would be 0.1 to the power 2 and divided by 2 factorial. So I am since this vec is a column vector, so I am using here I am taking dot products, like element wise dot product. So these terms would be this terms variable would be a column vector, and then I am adding 1 as my Maclaurin series has this initial one term in the beginning. So I am adding this one over here and taking sum of all the elements of this terms variable. And my true value is I am using the inbuilt MATLAB function of exponential to calculate the true value, and then I get my relative error as absolute of exponential value minus true value. Then I am just displaying it. So if I take only one term, so if I only use one term of the Maclaurin series, only the first term, so I have 1 plus fx 1 plus fh, that means 1 plus a. So I will be getting my true my approximate value as 1.1 and my true value is 1.1052. So if I also display error over here, fine. So my error in approximation is 0.052. Now if I increase the number of terms, I take two number of terms, then my error decreases. If I take three number of terms, then my error also decreases further. So the more number of terms I am taking, the more time my error reduces more. I can also calculate how much time I am taking for increasing these number of terms. So I can use this tick-tock command of MATLAB. So it approximates the tick starts a timer when tick command when MATLAB sees a tick command, and then it stops the timer when it sees a talk command. So I am only approximating my function over here. So I will start the tick command over here. And I'm time elapsed. It shows 0 seconds because it's very the calculations are happening very fast because the function is very simple. It's still 0 second. If I increase the number of this to 100, it's still 0 second because this is a very simple function. For very complicated functions, we get a large time. So also we are doing it in a vectorized fashion, so that also improves the uh, optimizes the function run, so it is very fast. If I try to run it using a for loop, then I think we can see that in a much better way. So I need to take my term. Where is my MATLAB not working? Okay, fine. So x bar is equal to x bar plus and also if I take my error, then that would be, let me calculate true value. Then my error would be absolute minus this will give me XP val, this will return, and this will return the error, this will be my time elapsed. We'll save this. So if I try to run it for 5 values, then my time elapsed is 0 and my average approximation is this. If I try to run it for 100, why is it going 0 every time? T start is equal to tick and talk. Okay. T start and is equal to this is not working. So yeah, if you see, now you can see if I run it for 100, if I run it for 3 number of terms, then my time elapsed is 0.0016. If I run it for 100 number of terms, so my time elapsed increase. Is it increased or decreased? Yeah, so it increases 0.0033. But my approximation error in a numerical approximation, okay, I can also plot that. So 100 for 100 experiment. So I can just take this thing inside the for loop and I can get my error for every value of n, right? So and this will be I will just remove this part. First let us run for 3 number of terms. Furthermore, let me make this also I, and this is I minus, okay, I starts from 1, so this should be I, this should be I plus 1, and this should be I. Fine, so this is I, fine, and I will take these two inside, so we can get the number of time used for each one of increment of h. I will also make this an array. Because true val is a single value and I was only writing exp val, so this is a vector, so that is why it was giving me an error, because this is a vector, this is a scalar, this is a vector. Fine. So I am running it for 3 terms, so I am getting 3 values, right? So this is the first term of Maclaurin series, just the constant term 1. This this is 1 plus a, this is 1 plus a square upon 2 factorial, this is 1 plus a 1 plus a plus a square upon 2 factorial plus a cube upon 3 factorial. And with each increasing number of term, okay, let me plot error also, so we can see. So each increase in number of term, our error decreases, right? Furthermore, our computational time also increases with start. Okay, yeah. So can anyone tell me what is the error over here? So this is, what is basically happening is I am just trying to add one extra term to the previous calculation. So my computation time required will not be that much. The computational time required will not change by a lot, because I am just trying to add one more term. My computation time will only increase for this term over here and one extra summation. I am not doing it on a loop, so that is why the computation time is like it's sort of constant. If I increase it to 10 number of terms, yeah. So you can see for these terms it's sort of constant. Then it again increases. Then it becomes very less for like next few terms, right? So because I'm just trying to add one more term, and then it depends on the time complexity of this factorial function. So sometimes it's taking more time, sometimes it's taking less time. So that is why I'm getting these abrupt changes. So if I try to plot these, first let me try to plot error with this number of terms. Fine. So for only single term, my error is very large. As I increase the number of terms, my error has started to decrease, and for later terms, it is not exactly zero, but very small number. So 10, 10 to the power minus 8, 10 to the power minus 9, 10 to the power minus 11. So this is practically 0. For this case, we can assume this to be practically 0. Fine. So right now I'm using a step size of 0.1. So if I go back to my presentation, yeah. So the more number of terms, the lower error we get. That we saw just now. And let us see this part. The smaller a, or the smaller this step size that we take, the less error we get. Let me try to do that. This one only. If I this will remain same. This, let us make this I. And let us also calculate the error. So I will move this to the top because we need this variable for calculating error. Then my error for each I would be same value xp val I minus q val. I will end this loop. So this is the display part. Let us now write the plotting part. We will plot back, then error, or let us plot with respect to all with error. Make line width 2 to get for increased visibility. And on a another plot, I will plot the fine. I will plot the log plot of this. Vectors must be same. All error. So my error is 1 cross 10. My AOL is 1 cross 3. Sorry. XP is 1 cross 11. Let me just clear the workspace. The issue was that I had not initialized these two empty matrices, so it was taking the previous ones. And I also need to true val xpa. Yeah, fine. So this should also be a all. is for n is equal to, I have taken 5 number of terms, so this graph is for n is equal to 5, right? And on the same plot, if I try to do it for, I will just put a hold on over here, and a hold on over here. We just close these plots and try to plot them again for different values of n. So let us first try to do it for n is equal to 2. So this is for n is equal to 2. Now on the same plot for n is equal to 3. So the bottom one is for n is equal to 3. And then for n is equal to 5. Why there are two values over here? Okay, I will add different plot points also. So just make this there are only 2 points. Why is it showing me only 2 points? For 1, I am getting 3 points, and on the same plot, if I run it for 2, then I am getting 3 points. On the same plot, if I run it for 3, I am getting 3 points, log plot. And if I try to run it for n is equal to 4, then I am only getting 2 points. The last value is being, okay, let us check the error value for the last part. Okay, for n is equal to 3, this is fine. I'm only getting 2 points. X 0.01, y this, x here is 0.1, so I am not getting the graph for 0.001. Why is that? Okay, my error is very less over there, so it shows me 0. So a log of 0 is not defined, so that is why. Yeah, so this is minus infinity, that is why that is not being plotted over there. For other values, like for n is equal to 3, this is like very small value, but still the the MATLAB. Let us talk about the machine precision of MATLAB. MATLAB has a base. MATLAB uses a base 10 system for storing the variables. Uh, the minimum number that I can store in MATLAB is, I type the EPS command. So this is the minimum number that I can store in MATLAB. Any number less than this, it just truncates it to 0, right? So if I try to store 2 to the power 2 to the power minus 16, sorry. So this number is basically 2 to the power minus 52. So if I try to type 2 to the power minus 52, so it gives me this. Now if I try to type 2 to the power minus 53, sorry, you see, this is okay, becomes less than that. If I try to make it 55, again goes further down. Again goes further down. But for numerical computation, it cannot store. Like if I type help, yes. The positive distance from to the next larger magnitude floating point number of the same precision as x. X may be either double precision or single precision. EPS with no arguments is the distance from one to the next larger double precision number. That is EPS with no arguments returns 2 to the power minus 52. So if I type anything, okay, should not give me 0 then. Does it give me? Let us just calculate the value like this. So exp val first minus exp minus true val. This is fine. Okay, this is for n is equal to 3. Let us try to do it for n is equal to 4. This just turns out to be 0. These two numbers are exactly same. Yeah, so up to 2 to the power minus up to 16 15 decimal places, these numbers are exactly same. So that is why we are getting a 0 while we are calculating the error. That is why we are not able to plot this plot the graphs after n is equal to 3. So for n is equal to 4, we are only getting 2 points because the last point is 0, and on a log-log plot, MATLAB does not include values less than 0 or less than 0. Truncates them, like it does not considers them. So that is why we are getting only 2 points for n is equal to 4. For all the values after this, I think we will be getting only 2 points. So if I plot it for n is equal to 7, yeah, so I'm only getting 1 point. So now this also goes to 0. For the second value also we are getting an error of 0. So you see, so for 0.001 the error is 0, for 0.01 also the error is 0, and for 0.03001 we got some very small value of error. So that point is being plotted over here. if I increase the number of points further, so all the 3 points goes to 0. Fine. Okay, so now what I was trying to say is for n is equal to 1, for n is equal to 2, for n is equal to 3. Okay, so let me also add. So the first one is for n is equal to 1, the second one is for n is equal to 2, and the last one is for n is equal to 3. So as more and more as we decrease the a value, so the first one is the first point is for a is equal to like for or a or for h is equal to 0.001. So this is the first point, approximation with only using I think no. So, yeah, so this is for 0.001, this is for 0.001, and this is for 0.1, right? Fine. So as we decrease the a value, the error decreases. So you can see over here, this is the largest a value, this is the middle a value, this is the smallest a value. So as a value decreases, the error decreases. Furthermore, as we increase the number of terms, the error also decreases. So this is for n is equal to 1, this is for n is equal to 2. So the error has decreased across all the a values for increase in number of terms. Similarly, as we go from n is equal to 2 to n is equal to 3, the error decreases. As we try to increase the number of terms further and further, the error further decreases. And since MATLAB can only takes into consideration numbers which are up to 2 to the power minus 52, if a number is less than that, then during calculations MATLAB truncates it to 0. You can see I can type the number over here and it stores it completely fine, but during calculations MATLAB just truncates number less than 2 to the power minus 52 to 0. That is what we saw with n is equal to 4, 5, 6, 7, like that. Okay. Furthermore, now like if I go back to my PPT, so my order of approximation is a to the power n plus 1, right? So on a log plot, this order changes to like my slope should be n plus 1. So if I take a log of all okay, let me, how do I write that? So e to the power this is my true value. So if I type okay, let me just type, that would be much easier. Discard. So my t minus approximate, let me write that as, so let me type this as true minus approximate, and that would be my order a to the power n plus 1, right? So I'm taking all of these terms over here. So my true minus approximate is this. Now if I so this is my error. If I take absolute value of this, so this is my absolute error. Now if I take log of both the sides, then I can write this as my log of error and I can also take a log this side. So it's not exactly equal to, but some sort of approximation. So we'll just use a tilde over here and I can write it as n plus 1 and then order of log a, right? So on a log plot, this should on a log plot, this is like y is equal to mx. So this should be my slope on the graph, right, of the order n plus 1. So if I go back to my graph, so this is like for n is equal to 3. So this is my first point. This is my second point. Right. Now if I calculate the slope of this line, then that should be that should come out to be 4, around 4, right? So if I do that, so this is last one I plotted for n is equal to 3, right? So I will just take that only. So slope is equal to log log of yeah, so error divided by log of a value, right? So log of error and minus log of error 1 divided by log of, so my first value is a all this is the n minus log of a all on the first one. Yeah, so I'm getting a number that is close to 4, as I should get like it should be n plus 1. So my n is equal to 3 for this this line, so I'm getting a value that is close to n plus 1 or 4. If I try to do it for n is equal to 2, so I'll just change the values to for n is equal to 2. And now if I try to do the same thing, so n is equal to, so I'm getting a number close to 3, right? Similarly for n is equal to 1, I should get a number that is close to 2. So I'm getting a number close to 2. Fine. Okay. Yeah. So we saw that the more number of terms we take, the lower the error is, and the smaller the value of a we take, the lower the error is. Let us now go to the next section. So professor also told something about numerical differentiation. So we can simply calculate it using the Taylor series only. You can see over here that f of x plus h is equal to fx plus h fx. So now if I try to if I want the first derivative of this function, so I can just simply remove all these terms, truncate all these terms, and I can just consider these three terms. So if I take fx over here, then that becomes fx plus h minus fx, and then I just divide it by h. So that is my fx, and if I take a limit of h tending to 0, that is for very small value of h, then I can approximate my fx as this, right? So yeah, let us see an example for this also. I will create one more script. So the value is what was the example? Okay, let us do this for tan. Yeah, for tan x. I think it was tan x maybe. Yeah. So tan inverse. I think what was the example? Yeah, tan inverse. So my true value would be so in this case my my a would be whatever x value for which I am trying to approximate the tan inverse. So that would be my a, and let me now take h values. So try to do it for different h values. Minus 4, minus 3, and 1a minus 1. So the four values is 0 0.0001, 0 0.001, 0 0.01 and 0 0.1. Let me also initialize. Okay, so let me take this to initialization only. Let us try to do it for pi by 4. So let's try pi by 4 over here. If I try to run this, so my true values this. Fine. So this is my true value and this is the approximated value. Now what we need to do, we need to write a, so my fx would be like a tan, right? So if I, for different values of h, will be the same, similar to x bigger. the more I decrease my for 0.1, my error is 0.0293, and for 0.01 my error decreases further, and for the okay, I will zoom it over here. So for 0.001 my error is even less, and so the more I try to decrease my h value, the closer I get to the true value. So if I try to decrease my h even further, 0.8, make this 0.8. Yeah. So the value is 3.88 10 to the power minus 9, so it is even closer to 0. Fine. So that truncation error decreases with h. So the smaller the h we take, the smaller error we get. And machine precision may determine how small h we can use. So yeah, like I showed you in the previous case, for the McLaurin case, the difference that the difference that MATLAB can calculate is should be of the order should be of the order to greater than 2 to the power minus 52. If the number is less than that, then it will just make that number 0, right? So if I take a very small value of h, then it will just decrease that even further, and it just goes to 0, right? So that is what is meant by machine precision may determine how small h we can use. And round off error increases with h. So yeah. So the more the higher my h value is, the more is my round off error. Okay, if I try to plot this, so yeah, we can see it over here only. Our order of the slope of my graph, the differentiation graph should be of the order h, right? So fine. That is why the lower the h we take, the lower the truncation error becomes, because this order becomes smaller and smaller, right? Now let us go to the next part. Yeah, let us go to the iterative methods. So until now we were looking at the direct methods, where we had a formula for the we had a we don't have to do any initial guess. We just had a formula. We put in values in there, and we were getting a value. So the my our variables that we could change were the step sizes, or the h values, or the a values that we can take. But in the iterative methods, we have an initial guess, and then we try to then we have an algorithm, where, like, suppose if I look at this square root formula for square root of 2, then this is the formula for square root of 2. This is called the Heron's algorithm. So I take a current estimate of x, and then I calculate this variable, this value, and I try to store it for and I take this value, and that will be my next x value. Then I again iterate it, use the current x value and iterate it to calculate the next x value, and the loop continues until I satisfy a criteria that is called my convergence criteria, right? So if we try to look for this, then if we try to code this, so let me just read this part. if I try to look at that, then I just need an initial guess, right? So I will just initialize my x to some value 1. Then if I want to run my iteration 10 number of times, then I will just run a for loop is equal to 1 to 10, and my next new x would be x is equal to what is the formula? 0.5 multiplied by my current x plus 2 divided by my current x, right? And so this will just okay. Let me try to store the values also. So what this will do, this will create, I have made x as an vector, so it will just use the current value of x and store it in the next element of x. Calculate error also, so my true value for so this is not my true value, this is how MATLAB calculates it, calculates the square root of 2, so I will be just using that as my true value. So this is this value 1.4142 rest. So I will run this algorithm 10 number of times, and I will see how close I am to the true value, right? So I will calculate my error. Let me initialize error also. So I am initializing my x to 1 right now, and my error vector is empty. So this will be absolute of I plus 1 minus true value. be much better. So I initialize it with 1, and after first iteration my value is 1.5 and my error is 0.08. For after second iteration my current value is 1.416, my error is this. So if I plot it, do I need to plot number of loops? So 1:1 and error. So this I will plot on line with 1.5 and plot on a new figure. I will plot the next graph. So this figure 1, figure 2, figure 2, and I will plot my current value on this, right? So this will be my x. On the same plot I will plot the true value. So that would be variable from 1 to n, and multiplied once of 1 to length n, just multiply it by my true value, right? Dash dashed line, and with a red dash dash line. Student true value into 1 into length n. Sorry, n is a scalar. This must be same length 1:1 x. So 1:1, what is the size of my x? It's 11, and this is n is 10 only. Yeah. Fine. So this is my error. So as the number of iterations increase, my error goes close to 0, not touches 0 exactly, but it goes close to 0. and this the red line is my true value, and the blue one is my approximated, or my value after these running the Heron's algorithm. So first I initialize it with 1. After one iteration it goes to 1.5. Then after second iteration it comes to 1.4, and so it is close to it oscillates about this line only. So it goes closer and closer to the line. After certain value, yeah, so this error, it's order of 10 to the power minus 16 only. This is minus 16. Minus 16, so the error sort of yeah, becomes constant after a certain value. Okay. So right now what I'm doing is that I'm using a for loop to run this loop. So to run the iterations a defined number of times. So I'm trying to run the iteration 10 number of times. What I can do is I can put a convergence criteria and stop the for loop, or stop the loop, not the for loop, or stop the loop if the convergence criteria is met, right? So instead of this, if I put a convergence criteria or a tolerance value as it is called, so if I put a tol as 1e minus 6, right? So if my error is less than this, then the loop is stopped. So instead of for loop I will use a while loop, because while loop runs until a condition is met, right? So I will run a while loop. I will put so error until my error is greater than my tolerance value. This loop should run. Okay. And since I'm using I'm storing every value of I, so this should be the latest I value. So my error is an empty vector. If the loop runs, the value is getting the value is getting entered into the value is being entered into the error vector. So using this line of code, I am using the latest error value, or the last element of the error vector, right? So if this is greater than my tolerance, then the loop should continue to run. And I can simply use a count variable also, so to get how many times my loop ran. Or in this case, since I'm storing all the values of x and I, so I can just get the length of this error vector to know how many times my loop ran, right? So so I need to initialize it with some variable, because initially it's 0, so there is nothing to check the value this logical statement with. Okay, so I will just initialize it with some large value, and 1, a value greater than the tolerance value. Okay, now this should run. Okay, so I is not defined, right? So I need to initialize I is equal to 1. Since I is not defined anywhere, so that is why I'm getting this error. So I am initializing I to 1, and then after every calculation I will just increment I. So for next loop, this I will go to I will become 2, and so this will be stored in the next element. Okay, so n is not defined. Okay, there are a lot of n is not defined, so n should be number of times my loop ran. So my I is 5, and my error vector is also 5. So this is also 1 cross 4. My I is 5. I initialized with 1. So this should be 1 is to I minus 1, and this should be 1 is to I. Should be 1 is to I. This should be 1 is to I. Let us check this now. Yeah. Okay, so I think I need to close the figures for plotting the next one. Okay, so right now I'm using a while loop to do the same thing. So I can see the loop runs 4 number of times. So after 4 iterations, I am able to meet my tolerances. So the loop exits, or the and we get these plots, right? These plots are similar to what we were getting in the initial using a for loop only, but the loop stops after 5 iterations instead of 10. Okay. Right. So with this, we have some time left. So let us now look at the this non-graded assignment of for week 3 and try to solve this. This is similar to what we have seen until now. Thus the code just the functions are different, right? So we will try to do this, and over the next half an hour, right? I think I have half an hour left. So first problem 1, a non-convergent infinite series. So all the examples in the course are non-convergent series. In this example, you will see a code. We will code a series that does not converge. And so write a MATLAB code that takes the values of n and returns s. Please record these values below. Takes the values of n and returns s. Okay. So let us write a function. Our input should be n. Okay. This is nothing. We will just value is equal to let us initialize sum to 0. Then let us run a for loop n number of times, or we can do it without for loop also. So if I take a vector then Square root of the elements of x. Then why is it not giving? Okay, it is p. Sorry, I was using the wrong way. Yeah. So this gives me the square root of all the elements of v, right? But since I'm trying to so this is like square root of this would be a vector, so I'm trying to do an element wise operation. I need to take a sum of all the elements, so I need to do an element wise operation over here. So 1 divided by square root of x, so this will give me a vector which with these elements, right? So now my value should be I don't need to have a sum, so my value would be 1 plus sum of all the elements of this, right? Fine. So if I take two elements, okay, let me save this also. Series sum. So now if I take series sum of 2, then that should give me 2.4142, right? And okay, yeah. If I use 2, then okay. Yeah, fine. So okay, since I already have one over here, right? So if I'm using 2, then this already have one over here, so I need not to add this one over here. I just need to take a sum of this, right? So now if I run it series sum 2, then I should get 1.7017. I need to report the value for n is equal to 10, so I will just run this for, we will enter 10 over here. We will enter 10 over here, right? And it is mentioned that we need to report the answer to 4 significant digits, right? So in this case, 4 significant digits would be 5.021. Okay. 5.0211. Now for 100, so the same thing for 100. 500. And for 1000. 5.896, so I think I can just write it 5.59. Now if I try to plot it, so if I run this for 10,000 number of times, okay, you see, uh, the series is not converging. Okay, for like 10,000 up to 10,000 numbers also, this series is not converging. If I run it for more number of times, this will take time. I think I entered a very large number. 4, 5, 6, 7, 8. This is also taking time. 10,000. So now 100,000. 100,000. This is taking a lot of time. So until this runs, let us check the next question. So we used the iterative method to calculate the square root of on a number of lectures. In this problem, we use the iterative algorithm. Cube root of 5. Formula is given this. The initial guess for starting the code is 0.05. The iterations run as long as the absolute error exceeds a given tolerance. Okay. The code should stop and return the result as soon as the absolute error falls below the above tolerances. The code should also return the number of steps required to compute the cube root to the desired tolerance. Okay, fine. We can just change. I don't know why this is taking so much of time. For 10,000 it ran fine. For 10,000 this is running just fine. For 10 to the power 5 also this takes time. Okay. So probably because my system is slow, that is why this is taking a lot of time. So you see still the series is not converging. So for for yeah, for 10,000 steps we were somewhere around here, and for 10 to the power 5 we are somewhere around there. So still there is no sign of convergence. So the series is not converging, it's a diverging series, right? Fine. So for the problem 2 we can just simply change the Heron's formula, the algorithm, Heron's algorithm. just copy this entire thing. For cube root. Okay, so this is for cube root. So for cube root of 2, right? Furthermore, the error that we were using over here for the square root was so this was not the absolute approximate error. So we have to if I go over here, yeah. So there is something called as approximation error. So the true error and relative error were the ones that we were using until now, or the one that we had that we have used in the calculation of a square root of 2. So we differentiate the current value and with the true value, and we get an error. But what this algorithm wants us to do is use the approximate error, or the error that is the difference between the current estimate and the previous estimate. So until those two estimates, the difference between those two estimates is above a certain tolerance, then the iteration should run. So yeah, so that is called approximate error. So a numerical value v is first approximated as x, and then it's subsequently approximated to be y. Then we calculate the difference between those two, and we get an approximate error. Okay. So this approximate error is usually what is being used in most of these iterative algorithms, because we don't know with certainty what is the true value of our function is. So we simply run the algorithm until the difference between the last two calculated values is below a certain threshold or a certain tolerance. Then we take that algorithm or the number of iterations as converged, and we exit the loop. Okay. So let us try to do that only. So I just copied the entire thing. We have it's mentioned over here that we should take our initial guess as 0.5. So I will just initialize it to 0.5. Okay. So for the first part, compute the cube root of a is equal to 16, accurate to a tolerance of 0.001. Okay, so this formula was for for cube root of 2. So for cube root of 2, we have 2 over here. This should be 1 by 3. This should be 2. So for cube root of 2, it should be 2 over here, and for cube root of 16, I should change this to 16. Okay. Now this should be whole square. Okay. 1 by third, 2 to the power x, 2 multiplied by x plus 16 divided by xi whole square. Right? Now I will calculate the approximate error. So instead of true val, this should just be xi. Okay. Now I don't need this true val. The tolerance needed is 0.001, and report the result res. Okay. Compute the cube root of period to tolerance, report the result res. Fine. So we need the current value of xi, also report the value of n and the number of steps required above. So that we can get that using this I value, right? So we are initializing I with 1, and after every iteration we increase this I, right? So either we can calculate the length of this error vector, because the length of error vector is similar to I, same as I, or we can simply output the I value. Okay. And yeah, these graphs, so we don't need these graphs now. Okay, or we can just simply do this. So if I calculate my true val, so 16 power 1 by 3. So I will run this section now. Yeah, so it has converged after 11 iterations, right? So the number of times loop runs 10, so it has converged after 10 iterations. We are seeing 11 over here because this one is the initial value, right? The first index is the initial guess that we have given, and the subsequent are the iterations. Okay, so the loop runs 11 number of times, and we need to output the value of report the result res. So we can just take the last value of x. Yeah, we need 4 significant digits. So 2.519. Okay. Now also report the value of n, number of steps required above, so that would be 10. So I can see over here after the 9th iteration my error is 0.5725. No, after okay. So after the 9th iteration my error is 0.0081, and after the 10th iteration the error drops below 0.001. So the loop exits. Now we need this for 27, so I will change this to 27, and tolerance is 1e minus 7, 1e minus 7, yeah, 1e minus 7. Fine. So I will run this section. Okay, if we want to see the plot, then we need to change this to also 27. Okay. Fine. So after 12 iterations, this converges, or the error becomes less than 1e minus 7, and the program converges. So the final value, that would be our end value of x, yeah, 3. Okay. So if I enter format long, yeah, still it's 3. Okay, now this is the smallest error in differentiation. So use 3-point backward difference formula for finding f of f dash x. This is the formula. Calculate the differential for 2 to the power x at x is equal to 0.4. Right, so let us create a new function. So our function should take as input the value of x and the value of h. Okay, because we have only 2 parameters in this formula, so I will take as input x and h. Then I just need to write this formula. So I diff function handle, function or can just simply write it because it's a simpler function, so I don't need a function handle. So let me just write as 3 times 2 to the, okay, let us make this function handle only, because then for some other function also we can just simply change the function handle and the code will be same, right? Otherwise we need to change lot of things. So I will not make this y, I will not make that x, I will make this as y, 2 to the power x. Okay, now my diff value would be so 3 function, first is x, then minus 4 times function x minus h, then plus function x minus 2 times h. Okay, and I need to divide this by 2 times h. Fine. Okay, so yeah, this should work. And so I will save this function. Now I will just create a script. So I need to perform the calculations for different h values. So let us just create an h vector. How shall I create this? Now my h all should be 10 to the power element wise power I. Okay, no, sorry, minus I. Let me just check if this is correct or not. Yeah, so this is fine. Okay, clear the workspace. Now my true value. So my true value is so by default log is base e only. If I write help log, so by default this is natural log only. If I want log 10, then I need if I want to calculate log base 10, then I can use the function log 10. So there is a function called as log 10. So okay, help log 10. So this is base 10 logarithm. Fine. So log of 2 multiplied by 2 to the power x is 0.4. Okay, let me make a function for x only. X is 0.4. So my true value is 2 to the power x. Okay, now please report the approximate value of f dash x at x is equal to 0.4 to h is equal to 0.1 and using h is equal to 0.1. So for the first part, I just need diff y1 is equal to also report the error for the above, and we can calculate the error using ABS trueVal minus diffval1. So this would be our error for the first part. So I will just write error 1 over here. Please report the so let us just like this week 3 diff script. So if I run this, I get my error, sorry, error 1 as this. And I also need to calculate diffval also. So diffval1. So the function gives me a diffval value of 0. Okay. Okay. And my true value is 0.9146. So my error would be 0.9146. Then I will report now I need to run this whole algorithm for all the values of h. Okay, so I will just run a while loop for j is equal to 1 is to adding gth h all. I will store the values. Second part. I will initialize the variables diffval2 and error2. I just need to run the same thing for 10 for this 8 number of times. So diffval2 I is equal to week 3 function diff x would be same, and my h all I. Fine. Then similarly my error 2 I would be okay, is the true val minus diffval2 I. Okay, and I will just plot this to simply check. We can just use the min max also. Let us do that only. Val index min error 2, and we need the h value for that index. Okay, so h all index. Also report the minimum error, so that we will get from this. So let me just write this as error min. Okay, this should work. Let us run this and see. Sorry, this should run. Diffval I length all. So h all is 1 cross 7, and diffval2 is empty array. Why is this giving me an error? j, not I. I have a habit of usually indexing the loop variable as I, that's why. So we have already used I over here, so we have used the loop variable as j, so it should be j. Let me remove this breakpoint. Undefined function default to for input arguments of type double. This is something new. Defined function default default to true val. True val is already defined. Error. So now this one's fine. So error min is this, and it happens for h minimum of 0.01. Okay. We can also see this using the plot. So if I plot h all versus error, error 2. There are a lot of plots. Okay, so something is error 2. I am getting same error for every variable. Why is that happening? Default to j, error to j, true val, nested val, v3 function diff. So is this right? 3 times of function x minus 4 times of x minus h plus 4 times plus function x minus 2h divided by 2h. So this is fine. X is 0.4. True val is log 2 into 2 to the power 0.4. Okay, why am I getting the same value every time? If I because of error in this, so this should be y. I typed x only. So using h is 0.01. If I calculate the error, then my 0.9145, and my error would be so I need to give 4 significant digits, so 0.00001457. Fine. Now if we run this part, then it should give us the correct value. And error min, yeah, okay. And if I plot it, yes, no, nothing, no plot open, right? Fine. So minimum is for 0.001, and afterwards the error again starts to log. Yeah, this is much better visibility. So the minimum happens at 10 to the power minus 5. Similar value we are getting over here. So this is like 9.999 or 10 to the power minus 6. So that's 1 to the this is 10 to the power minus 5 only, right? Yeah. So here we get 10 to the power minus 5. Now the minimum, also report this minimum error. So this minimum error is 1.547 and 10 to the power minus 11. So this one. Okay. Yeah. So this is the fifth value only, right? Fine. Now let us go to the last function. So download the file and use it as a template. Okay. Just copy this. In this problem, you will use Maclaurin series until the nth order term I terms up to x to the power minus n to compute approximations of hyperbolic sine function given by this. Note this x is in radians. In the template, you will find vector vec. Okay, so here we have a vector pre-computed for you. Please use this vector vec to compute approximate values of sine hyperbolic x. Your function should return sin h val while taking the values of x and n as inputs. Fine. So please don't edit anything. You may start editing. Fine. So we yeah, so we have this vector already with us. There's nothing we need to do. We just need to take a we need to take alternate terms of this x. of this vec vector, right? So the first term, the second term, the fourth term, likewise. So if n is equal to n, then we need to take terms up to we will start with the second term and we will go till nth term. Okay, so sin h vec would be we will take vectors from this vec. Fine. So we will start with the second term, that is so this vec starts from 1x x square divided by 2 factorial, and likewise. And for calculation of this sine hyperbolic, we need the x value, then x cube divided by 3 factorial, and likewise. So we need the second value of vector for of this vec vector, the fourth, second, third, fourth value of this, and sixth value, likewise. So we will take out elements from this vector, starting with the second element up to nth element in increments of 2. Okay, so if I write it like this, so 1 is to 10, so my I is a vector from 1 to 10, and now if I take j, that starts from this I, from the second value of I, take increments of 2 and then go to 10, and I should get 2, 4, 6, 8, 10. So likewise I need the even elements of this vector. Okay, and now my sin h val would be just a sum of this sin h vec. Okay, yeah, so I need to just return that part. I will save this. Now report the results on running. Sim h val is equal to ml sin h 2.58. So I will just copy this, run this. So this is, I need 4 significant digits. 3, 0. Okay, leave this one. MATLAB function to calculate the true value sin hx. Calculate and report the absolute error with the true value between the true value and sin h value calculated in the question book. Okay, so I will calculate true value sin h 2.5. And now my error would be absolute of true val minus sin h val. Okay, so this would be my error 0.01113 up to 4 significant digits. The same code for 1.4 and 5. Okay, so 1.857, right? Also report the absolute error. Please report the 4 significant digits. So I need true value for 1.4. Okay, and now my error will be 0.00. So 0.04696 up to 4 significant digits. Fine. So this is the graded assignment, non-graded assignment 3. Yeah, so I think we have already exceeded the time limit. Does anyone has any doubt in any of these questions or problems that we have discussed? So you can ask, otherwise we can close this interactive session. Hello. Yeah, you are audible. Hello. Yeah. Mm, yeah. Yes.
Sir, can you
So
just
this,
put the main file of this, the call?
yeah, this is the calling file.
So now here we wanted to find which values of h is giving the minimum error. So
Yes.
you have used the help of graph and commented. Uh, my query was, can we now here no, we
What
have
can we?
minimum error.
Yeah.
Let us suppose j is running from 2. Now j is 1 to length. No. If I am going to give j running from 2 onwards, because I was also trying this problem last week, just
Hmm.
a second, yesterday. So
Yeah.
I just take underscore j is running from, or I can say I is running from 2 to 8. So, but when I was using this code to find minimum, it was giving 0 because I have started from I equal to 2, no? So for I equal to 1, it has taken by default as 0.
Yeah,
And
because okay, yeah. So suppose you
my
have,
question,
okay.
my question is in this:
Hmm.
can we start from 2 itself, and can we try to get the minimum value instead of starting from 1? Is there a possibility?
Okay, let me just run this. Okay, let me just run this and try code. Yeah. So now my h. So this h. This is like from. Uh, okay. I is a 1 cross 7 vector. Uh, so
So what I'm
you
trying
were saying that instead of j you were initializing from I,
I
and
and yeah. So just the first section, if you kindly go.
no, yeah, if I change I over there, then everything would be I, no?
But we should start from 2 because we are having this h bar 10 power minus 2 now. So when I was giving I starting from 2, it was taking by default at 1 0. So can we avoid it? Means is there any way where I
Mm,
can start with the 2 itself and I'll be able to get the exact answer, the error?
okay, okay. No, because see, if you take two over here, then this the error, right? So it will initialize from it will the error value, calculated error value will be entered into the second element of error two, right? But your error is a what you can do is simply create a error vector. Okay, if I create this error vector using ones of 1 cross what is my size of I think it's 7, right? Yeah. So if I make this as 1, so I just need to have some error value, some initialization of this error, such that it's always greater than whatever error I am getting. Fine. Uh, so right now if I initialize it using 1, okay, and now if I run the script, error must not exceed 7. Okay, why is that happening? Uh, this is what you were doing, right?
Yes, sir.
Uh, why is it giving me this error? Okay, so h all instead of right. So this should not go to. So this should be I initializing. So I minus 1, and this can be anything. So I think what the issue is that I'm initializing. You were initializing diff val to an empty array, and error also to as an empty array, right?
Uh, Actually, yeah, yes, sir. Yes, sir.
Yeah. So the issue is when you initialize it using an empty array and you are just directly trying to access the second element or any other element of the array uh, by uh, by not by like you are trying to pass the first two elements and directly pass the first element and directly access the second element. So it just enters a zero value for the first element. So if I initialize the entire vector or even the first element to some higher value, like 1, and then I try to calculate the other thing. So let me just initialize my diff val as zeros, 1 comma 8, and my error as ones, 1 comma 8, and I am trying to access the fourth, the third, the fourth, no, yeah, the jth minus 1 element, and this should access the second element. This should give me the first element, and this will be the second element. This, yeah. So now this runs. Now my h min, if I try to see, so this is this. What was the h min that we were getting previously? I think, yeah. So the index is fifth only. Sorry. Let us make a log plot of this. Yeah. So if I initialize them properly, then still I am getting my minimum at 10 to the power minus 5 only. So what I have just done is I have initialized my diff val to a 0 vector, and I have initialized my error as ones, because see, what the issue was with your code was that you were directly trying to access the second element. So the first element, MATLAB already makes that element 0. Now whatever other errors that you were getting, they will be greater than 0 only, right? Because they were of the order like 10 to the power minus 6, minus 7, minus 5, minus 2. So all of those values are greater than 0 only. So what I just did, I just tried to initialize error with a number that is much greater than 0, or much greater than 0, right? Yeah. So I initialize it with 1. So all the other orders of error value that you were getting are very less than 1, right? So I will get my minimum in the desired location only, where it's supposed to be.
So it means, let us suppose we have got the same question to go for maximize, then I can think of initializing the entire vector to 0.
Yeah, then 0 would be better, because all the other errors would be greater than 0, right?
So can you just scroll up, sir? I will just fix it. Part one.
What?
Can you just scroll up, sir?
Scroll up, okay.
Yeah, scroll up. Further. Thank you, sir. So one kind request. Actually, even professor also has recommended some textbooks, reference book, but I was googling it. All we cannot access due to one or the other reason. Is it possible from your end that you can,
Okay.
give
Yeah. So, are you able to access the Google Drive?
Google Drive? Yes, I think recorded videos, sir. Like not
Yeah, the
recorded.
recorded videos, but there is a link for Google Drive also, where the PPTs as well as the codes are given.
Yeah, PPTs of the concerned faculty. Am I right?
No, not the concerned faculty. Okay, let me just share that PPT with you guys. Just share that link with you guys. I will just see. Okay, no, Gmail. Where is it? I think. So this is the sheet now. So all of you guys are able to see this sheet, right?
Yes, yes. We
Yeah.
are
So in this,
started.
the first one is from Shayyad Sabir, I think. The second one is from Sandra, and the last one is mine. So yeah, you can see the codes as well as the PPTs over there. So I will also upload the books over there.
Yeah,
Fine.
it helps.
Yeah. So I will make one folder for books and I will upload the books over here.
Yeah, please.
Yeah. Okay.
Both with respect to MATLAB and even the numeric analysis with this numerical method so that we can get enough concept.
Yeah. Okay. Just try to see if you. I think you should be able to access it. I have already made this a shareable link. Okay. Let me copy this from here itself so you can. Yeah. Meet. Here is the chat. Just see if you are able to access this.
Yes, sir.
Yeah, fine. So I will make a section of books, and
Yeah.
I will upload the PPT and code for week 3 also over there on. Okay. Yeah.
Thank you. Thank you very
Okay.
much.
Thank you everyone.